Let's begin. We're almost done with ordinary differential equations. Quite a feat doing this in, almost a month and a half, 6 weeks, right? About it. Quite a feat. We've gone a long way. So here's one way to measure yourself. A simple question. Ask yourself, at the beginning of the course versus today, did I learn anything? Did I improve my learning if I knew the things that are being taught? And hopefully that's a positive thing. Yes, hopefully the answer is yes. I see many nods. All of you nodded, so yes. We're still kind of in the tools world, right? So we're learning tools to solve these problems. I'm trying to put in insight from the physics into these problems as much as I can. After we're done with ordinary differential equations, there will be more focus on the physics, but more so the mathematical physics, like how to describe a certain physical process with mathematics and then looking at the mathematical features of those physics. Because math is always reliable. Math is always reliable. You can always go back to the equations and narrow things out or put your assumptions in there and see what the equations are trying to tell you. Sometimes you don't see the answer directly from the equations, so the same Navier-Stokes equations could create counter-rotating vortices or vortex filaments, and you just don't see them from the equations. You have to understand the physics to see them. That's this thing that Richard Feynman actually talked about, having enough expertise to see the physical phenomena show up directly through the equation. So it's a skill, it's an acquired skill that over time you will develop. I released homework 5 today, although it's going to be it's going to be related to the topic we're going to discuss today, but it will combine initial value problems and boundary value problems. So that gives you an initial boundary value problem, which is what? A partial differential equation with time and space. You need an initial condition for time, you need boundary conditions in space. But you will see how unbelievably easy it is going to be to solve a partial differential equations with the tools we have. We're going to dig our heels deeper after we're done with this in the next unit of this course when we hit partial differential equations. But I just want to give you a flavor that you can do a PDE today with the tools that we have. It literally, the solution literally about 5 lines of code, excluding all the boilerplate and setting up the domain length, etc. But the actual solution to build the system of equations is no more than 5 lines using solve IVP. And I will guide you, the homework will guide you, follow the homework, and you'll have this eureka moment. That's the technology or the technique that we will use moving forward, and that you will use next semester with Professor Sutherland. So and Professor Yachau, there's a direct coordination of efforts between what you're learning here and what you're expected to know with Professor Sutherland, so you can hit the ground running over there. So that's kind of how we're designing things. The last time we left off talking about some more options with solve IVP. One of them was events, which you will use in this homework, actually, homework 5. One other option is called max step. Although this doesn't show up directly in the list of options when you look at the API of the solve IVP, but at the bottom you will see there's like a star additional arguments. Those are like nest deeper arguments that go into whatever solve IVP is using from external libraries. Anyway, one of them that's consistent across any of the methods you use, BDF, Radau, LSODA, or RK45, or the standard integrator, is max step, and that allows you to set a maximum limit on the time step size. Remember, solve IVP, if you don't give it, solve IVP by default is going to try to determine time step sizes on its own. There's a smallest time step size, and it can take large time steps. And so sometimes you would see it would solve the problem if it's really easy and linear. It might take 3 time steps. Then we said, okay, you can pass a t-eval or a dense output to get a smoother curve, but internally it is still evaluating at those 3 time steps. So it's not increasing accuracy in that sense. It's only choosing its own time steps and then building a polynomial to give you that sense that you have a smooth curve. One way to circumvent that is to tell it, no, don't take, I want to limit the biggest time step that you can take. And you can specify that with max time step. This is a physical time step in seconds. So that's your delta t. And you can tell it, don't go, if you can integrate this at 1 second steps, I don't want you to do that. I want you to do it at 1/10 or 0.1 seconds, right? And then you will force it to go and do integration at those steps. So you will circumvent what it wants to do. Okay, now obviously this max time step is fraught with issues if you don't know about time integrators. So you can mess around with it, and then if you see kind of weird results, try to play with that a little bit. It's an option out there. You don't have to use it, but if you know more about time integrators, you're welcome to use it. All right, we're done with initial value problems. Next, we want to talk about boundary value problems, which, as we described earlier, these are ordinary differential equations, so they're one-dimensional, but in space this time, where you are only given conditions along the boundary of your domain of interest. So it's like saying, I want to know what's inside the room given only the conditions around the boundary of the room. Now, this could be in higher dimensions. It becomes a partial differential equations only in space. We will talk about that later, but it's still a boundary value problem. You're only given conditions along the boundary. So that's the classic problem that we solved, where we had like a heated rod, and there was either we did some heating in the middle or some radiation environment, or this one you did in the homework, which we had convective heat transfer, where you're blowing air to heat it or to cool it. And the rod is fixed at both ends. That's what matters. Those are the boundaries. And the heating over here is simply comes through a source term on the right-hand side. But what matters for this ODE, which is a condition on the derivatives, is that you're specifying what's happening at the ends. You're holding the ends at a fixed temperature or at something else that we will talk about. So this is a classic boundary value problem. And then you ask, what is the distribution in space? There's no time here. There's only space. What is the distribution in space for this setup? Okay, boundary value problems, you might ask, okay, is there an equivalent to solve IVP in Python? Unfortunately, well, yes and no. Solve initial value problems are much easier because you only have one condition that you're starting with, which is your initial condition. Even if the system is higher order, you have 2 or 3 or 4 initial conditions, if you had like a fourth order system. But then you convert that into a system of 4 first order ODEs, each has an initial condition. So it's a really kind of well-defined, because you have one condition to start with and move on, integrate until whatever you want. With boundary value problems, because you have, at least in 1D, because you have 2 conditions, one on each end, they're harder to describe and solve generically. Okay, in Python, or the method, one method that exists in math, the only method that is that would try to make this as generic as possible and not problem dependent, is called solve BVP, and that's based on what's called the shooting method, if you've heard of that in any numerical methods course you've taken. So essentially, it tries to cast the boundary value problem as an initial value problem, and it starts from one condition, let's say on the left of the heated device, and tries to find the solution by kind of trial and error to hit what it needs to do so that it gets to the other boundary condition. Okay, it's it's a little bit hand wavy, but it does work for one-dimensional problems. But that's about it. Unfortunately, it is not robust. It only works for 1 dimensions, and it's really cumbersome to use in Python itself. It's very like solve IVP was really easy. You give it right-hand side, initial condition and integrate from 0 to t0 to t final, and you're done. Solve BVP is kind of convoluted to use in Python, so we choose not to use it. We're not going to use it. I don't recommend using it. A better method is to use finite differences to approximate derivatives and turn them into algebraic equations, as we will see later. The only catch there is that you have to, each problem is going to require a different approach to solve it. So with solve BVP, the shooting method, it's a standard approach. It's generic, but it only works in 1D. It's convoluted. It's not very robust for higher dimensions. Finite difference, you have to do the work for each problem you're working with, because you might have an additional derivative. You have to discretize that and convert it and set the boundary conditions and write the system of equations. So you have to do the work per problem. However, it's very robust. It's easily extendable to 2 dimensions, 3 dimensions, or any dimensions. Okay? So that's the method of choice, and that's the one that we will use. Now, before we get to doing that, there's a small little background that I want to build on a little bit, and that's the approximation of derivatives. So the word finite difference means you're taking continuous differentials or continuous differences. Because a differential or a derivative is the limit of 2 differences, rise over run, delta f over delta x, right? And you're taking that continuous difference and converting it into a finite difference where you have finite values not in the limit as delta x shrinking to 0. So that's what the word finite difference comes from. And the idea is we approximate the derivatives with approximations to the derivatives themselves. We did that early on. Now we're going to get a little bit deeper into understanding technically what we're doing. So as we did with time integrators, with a boundary value problem, we're going to take the domain and we're going to discretize it. Remember, you know the word discretization, which means splitting the domain into discrete points. We will always choose to have equally spaced points in this problem. The extension to non-uniform or non-equally spaced points is doable, but it just messes up the math, so there's no point in spending time on it here. However, so assume you have this domain, you've discretized it into your equally spaced points. You assign each one an x location, right? And the spacing interchangeably is going to be called either h or delta x. So they're both used interchangeably. And you're actually looking for these values of the function that would be the solution of your differential equation at those discrete points. Okay, so you see at x1, I have f of x1 that I'm looking for, and then at x2, I have f of x2, and so on. Now, for simplicity, I'm going to replace f of xi by fi. So whenever I put fi, that means this is f at xi. When I say f at I plus 1, that's f at xi plus 1, which is a distance of delta x away from xi. So fi plus 1 is located at f of xi plus 1, which is xi plus delta x. Fi minus 1, which is to the left of fi, okay, is located at xi minus delta x. So this kind of simplifies the nomenclature quite a bit, right? Now, on a grid like this, we can define all sorts of approximations to derivatives. So this could go both ways. If you know the values of f discretely, say you're doing measurements at fixed locations. Let's say I want to measure the airspeed from here to the wall, and I'm taking steps in half a meter, okay? And then I take a measurement half a meter. So I have a bunch of measurements, and the distribution could look some interesting distribution. And then you want to find the rate of change of the speed as we go towards the wall. So you know f in that case, you know the values of f, and you want to find its derivative or its second derivative for some reason. You have COVID cases per day, for example, and you want to find the rate of infection, right? How do you do that numerically? It's very simple, is you take finite differences. You take the difference between 2 values over the distance between them. So that's your classic definition of the derivative, f of x plus h minus f of x over h. This is the same here. fi plus 1 is located at fi plus delta x, or fxi plus delta x, so at any point here, over the distance between them. You can also define a different kind of derivative. It's also a first derivative, but it has more terms in it. Now, this is going to be a little more accurate, than this one. If you remember the error analysis we did at the beginning of the course, we were comparing two different types of derivatives. So this one has a little bit more accuracy than that derivative, and we'll see why in a second. You can also define second derivatives. You want to take, you know, just compute the sign, essentially how the function is changing. If you know f, that's great. But also, in cases where we don't know f, we want to find f, this is also going to be helpful, because that's what we are going to do with boundary value ODEs. We're going to take the continuous derivative, replace them with finite derivatives, and we still don't know what f is, but then see what happens. If we get a system of equations in all the f's, and we can solve them, then we can find all of those f's that we're looking for. Now, you can define all sorts of derivatives. I have two tables here for you. For first derivatives, I have a formula, an order, and some comments on it. Okay, this is the name of the approximation, and there's also a column here, constant spacing. So let's go through these. The first formula for a first derivative is fi plus 1 minus fi over delta x. That's your rise over run formula. In the limit, we say in the limit as delta x goes to 0, you recover the derivative. That's what you learned in calculus. You learned this formula. Then there's this thing called order. I'm going to talk about that in a minute, but this has to do with the accuracy of the approximation. The higher the exponent on the order, the more accurate the method is. Okay, we'll talk about order in the 2 slides. This is called the forward difference formula and does not require constant spacing between the points. So this would work for unequally spaced data. Let's say you're trying to compute derivative from known data. First data point is here, next data point is at 1 meter, the other data point is at half a meter. You can use this formula at each point. You don't require equal spacing between all the points. Then there's this backward difference formula. Instead of going fi plus 1 minus fi over delta x, you do fi minus fi minus 1 over delta x. Instead of looking forward, you're looking to the other side. You're looking to the left instead of looking to the right. Okay? And that's called backward difference. Is it useful? Yes, absolutely. This is going to be useful. And they're all going to be useful. It's of order delta x, same order. It's called backward difference because you're looking backwards. And it does not require equal spacing. Now, these three over here, they have higher order, delta x squared. Okay? Delta x squared. And we'll again discuss these are more accurate than these ones. By how much? Again, we'll discuss that in a bit. The first one is called central difference formula. So you're evaluating the derivative at point I, but this is blending the point to the right of I and the point to the left of I. So it takes fi plus 1 minus fi minus 1 over the distance between them. It's still rise over run, and that's the distance between these 2 points, right? But it's much more accurate. However, this method requires equal spacing between the points, between these 3 points, okay? This one and fi. Then you have a second order or a delta x squared order forward difference. So it's similar to this formula. This is a forward difference of order delta x. This is a forward difference of order delta x squared. But look at that. It reaches farther than the point to the right of fi. It reaches the point to the right of that as well. It's blending the point at fi plus 1 and fi plus 2. And there's also a delta x squared backward difference where you're using points fi minus 1 and fi minus 2. All of these require equal spacing. How do you use this? You just come to the table. If I tell you, okay, here's a boundary value problem, use delta x squared forward differencing on the first derivative and central differencing on the second derivative, you should know which formula to pick. You plug them in and you convert to system of equations. You see this procedure in the next slide. For second derivatives, we can also define forward, backward, and central differences of different orders. Okay, so the standard one we use and we like to use is this central difference for the second derivative. That's the one we've been using in all our work for the heat equation. We use a central difference approximation. fi plus 1 minus 2 fi plus fi minus 1. It's blending these 3 points at fi plus 1, and fi minus 1. It's called the central difference approximation for the second derivative. It's of order delta x squared. All of these points here require equal spacing. All of them assume constant spacing, okay? Between I plus 1, and I plus 2, all of them. So across the entire grid, the spacing needs to be equal. You can define a forward difference formula for the second derivative, and this one is delta x order, or you can have a delta x squared order. And notice, as you want to increase the order, you're looking at adding more and more points to your approximation, okay? And the way you can think about this is look at this and say, okay, my forward, one of the first derivative forward difference blends these 2 points. The backward difference for the first derivative blends these two. The central difference blends these 2 points, okay? For the second derivative, you have the central formula blending these points, or a forward formula blending this one, and this one, or a delta x squared forward formula blending this, and that. The width or the number of points you're using is called the stencil. You don't have to worry about that. The wider the stencil is, the more accuracy you are obtaining, okay, but the more cost this will cost you. That's enough for you to know now. What's up with this order? I'm talking about order, and you've probably heard, oh, these are first order methods or second order methods. This delta x has something to do with the error, okay? And the formal definition is that an approximation is said to be of order p. Bear with me. P can be first, second, third, fourth, whatever. It's an integer usually. An approximation is said to be of order p. It doesn't have to be an integer, but in general, if your methods are consistent, it is an integer. It's said to be of order p if the error is of order h to the power p. H is my spacing, delta x or delta t. This applies in time as well. And notice the power. This determines the order of the method. Now, what does this mean? It means that your error is bounded. The worst error that you can accomplish is h to the power p times some constant. The constant has to be of order 1, okay? But like 2h to the power p or 1h to the power p, okay? In other words, your error, what is the error in this case? The true derivative minus the approximate derivative is bounded by a constant times h to the power p. We say the method is of order p. Okay? So for example, the forward difference formula, f prime is fi minus 1 over h. If I put an equal sign, I have to add an error term here. And I say this method is order h, which we saw earlier here. Okay, this formula is of order h, or delta x. What is the power of delta x is 1? We say it's a first order method. It means the error changes proportionally to delta x. The maximum error you can commit is delta x. Okay? This method here, the central difference, has an order delta x squared, or in other words, it has order 2. So we call this a second order method. And the error is bounded by a constant times delta x squared. Why is this important? Remember, in the first couple of lectures when we were talking about error, we took the formula and we computed the relative approximate error. And then we said, okay, let's shrink h by half. And one of your colleagues made an observation. I think it was you. And you said, if we cut h in half, the error is also cut in half. Why? Because the error is proportional to h. Okay, so if you cut h in half, you're going to cut the error in half. So let's see how this works. So for example, for a first order approximation, such as this one, your error is bounded by c times h. This is a first order error. Therefore, if h is cut in half, you want to put more points in your calculation to get better representation of the solution. So what happens to the error? How are you shrinking the error? If you double the number of points, you're going to cut it in half. Okay? You're going to cut it in half. And probably better, but in the worst case scenario, you will cut it in half. And you can see this mathematically. If the error at spacing h is a constant times h, then the error at spacing h over 2 is approximately the same constant times h over 2. So what matters to us is not the constant, is the order. It's h over 2. Now ch is eh over 2. So you see at half the spacing, the error at half the spacing is equal to the error at full spacing over 2, because we cut it in half. Okay, what do you think is going to happen with the second order error? It's going to be cut by a factor of 4. Yes, thank you. So in a second order error, at spacing h, the error is ch squared. At spacing h over 2, you're going to take h over 2 here, and that's ch squared over 4, which is eh over 4. So you took this error at spacing h, and you cut it by a factor of 4. So then you see the power of using higher order methods. If I double the points, only just doubling the points, I'm going to cut the error by a factor of 4, not a factor of 2. So you get more bang for your buck, per se. Okay? That's about it about order. But know that a first order error means the error, a first order method means the error scales by just the spacing or whatever step you have, whatever control you have, delta t, delta h, delta x, to the power 1. And then what that means, if you double the spacing, if you double the number of points, your error is going to be cut by half. If a second order method, you double the number of points, it's going to be cut by a factor of 4. A third order method is going to be cut by a factor of 8, and so on. Okay? That's about it. All right, so we go back to our heated rod, and that's the equation we're trying to solve. I'm going to lump all of these parameters, HP over lambda A, into just one coefficient. I'm going to call it capital H. And this is the equation I'm solving, the second derivative with respect to space equal to some forcing term. And again, you see as if t approaches t infinity, then there's no more heating anymore involved. Then you just get d equals 0 there. There's no more heating. And at the left boundary, I'm putting a fixed temperature. At the right boundary, I'm also fixing the temperature. The first step is to discretize the space domain into n equally spaced points, okay, and assign an x value for each one of those. I'm indexing here from 1 to n because it's simpler to go from 1 to n than 0 to n minus 1. But in Python, you'll be indexing from 0 to n minus 1. Okay, so keep that in mind. And at each point, like we did before, we have an x value. And also, I want to assign a value of the temperature at each one of those points. Now, I don't know these values, okay? But I'm still going to apply my derivative approximation and see what happens. At the left and right boundaries in this setup, I know the temperature. So these are given to us, but I'm going to still keep them as part of my solution process. And then in the interior, I don't know what's going on. I don't know these T2, T3, and so on. But let's see what we can do with this. Let's just try it out. So now my first question is the governing equation that T double prime equal HT minus T infinity, is it valid at these points in the interior, even the boundary? Is it valid? Maybe. It's either yes or no. Of course it's valid. If it's valid on the entire rod, it's valid at a subset of that rod. Okay? Obvious question. Otherwise, that's not the governing equation. It's some other equation, okay? It's a subordinate equation or like something else. Yes, it is valid at each and every point. So if you take that equation and apply it at point 2, you say, yes, second derivative at point 2 is equal to h times t2 minus t infinity. At point 3, it's the second derivative at point 3 equal to h times t3 minus t infinity. That's, if this is not true, pack your bags and leave. There's no point in doing engineering or any of this, right? This is true. Okay, so now we're going to pick an arbitrary point I. Poor I, it's been chosen as the dummy variable for eternity, but we're going to pick a representative point. So I could be 2, 3, 4, all the way to the end. And then we're going to approximate the derivative. So what I have on the right-hand side, I don't have any derivatives here. So this is already in algebraic form. It's h times ti minus c. I can't do anything about this one here. But this is still a problem. Yeah? And since we're not doing analytical method, we need to do this numerically. So we will approximate this with our central differencing formula for the second derivative. So I put an approximation sign here because I'm not tracking the order of the error. So it's an approximation. And this goes as second derivative at point I. This is my stencil, I minus 1, I and I plus 1. So you can pluck that out of the table, put it here, and that's equal. I want it to be equal to h times ti minus t infinity. So now we went from a continuous derivative to a finite difference derivative approximation. Now this is my equation, and it's also valid at all of those interior points. Okay? It's also valid at all of those interior points. So we can rearrange this a little bit just to simplify the math. Multiply by delta x squared. And this is a linear equation. So we're going to put all the unknowns to the left-hand side and everything we know on the right-hand side, because I'm estimating this is going to be just a linear system of equations, as we've seen before. So you rearrange things, and you get this generic formula at each one of these points. We've done this before. Okay? We've done this before, except that in the past I gave you this formula. Now you just know that we were missing one step, where you convert the derivative into a finite difference approximation. And then at point 1, so you're writing the system of equations. At point 1, I know the temperature. I don't need the equation there. I don't need to apply the differential equation. I'm given T1 equal T left. At point 2, I'm given T1 minus 2, etc., etc. I know you might say, but I know T1. Why can't I put T left here and move it to the right-hand side? You can, but then you're only solving from 2 to n minus 1. Okay? And then to plot the solution, you're going to have to add T1 and Tn at the end. What I like to do, I like to include this in the solution itself, so that when I solve the linear system, I have this already included in there. Okay? So at point 3, and then you just apply this discrete formula, right? And we're back into, this is a system of linear equations, and the unknowns are T1 through Tn, or T0 through Tn minus 1 in your Python code, etc. And lo and behold, we've seen this. We've done this before. Remember what we did in September, right? And so, yeah, this is it. We've done this before. I'm not going to go through it. We will do it for the next set of slides. We're going to have to rewrite all of this. But you can look at your notes. You can pull up any of the notebooks where we did linear systems. And yeah, this is pretty much it for boundary value problems. You will apply this procedure over and over again. But there's one issue that I need to teach you about. So far we talked about one type of boundary condition where we fix the value of the dependent variable at the boundary. So anytime you see a fixed value at the boundary, it's called a Dirichlet type boundary condition. Okay? It's a dude, last name Dirichlet. I think he was French. I actually don't know his first name. Some people call it Dirichlet or Dirichlet boundary condition. It's a fixed value. So what you're saying, phi at the left side is fixed, or the dependent variable is fixed, and the dependent variable on the right is fixed. Now there's another type of boundary condition, and that's instead of specifying the value of phi, we specify the slope of phi. Okay, so we specify the first derivative at the boundary. Okay? And that's called a Neumann type boundary condition after John von Neumann. Okay? And in this case, you're specifying the slope at either the left boundary or the right boundary, and it's a fixed value, or it could be a function of temperature or something else. Anything is possible. You just have to figure out the math based on the problem. Here I'm putting constants, but they can be more complicated. You could have a blend of both. You could have Dirichlet on the left and a Neumann on the right, or you could have Dirichlet on the right and a Neumann on the left. Okay? For second order derivatives, or like the heat equation, what happens if you have two Neumann conditions? What happens if you only specify the derivatives? you cannot find a solution because your solution is going to be off by a constant. So we will talk about that when we get to math in the next set of discussions, okay? If you remember your differential equations, okay, so take a second derivative, you integrate it once, you integrate it twice, you need two constants, okay? So you need to have two different types of boundary conditions, a fixed value and a Newman condition, okay. We covered this, we know how to do this. We didn't cover this. So I'm going to teach you how we do this. There's also different ways for doing this because we're open to different types of discretizations. This is one type of approach that works and is consistent, but you can see other types. Don't freak out. You just have to redo the math. Trust your math, do it consistently, step by step. Write it down, don't wing it in your code. Write it down on a paper. Type it up, make sure you know what you're solving before you get to the solution. Okay, with Newman boundary conditions, so we're going to take the same problem we've looked at, and I'm going to keep the one on the left fixed, but I'm going to change the boundary condition on the right, and I'm going to specify a Newman condition on the right. So I'm saying that the slope on the right is big. Now, in terms of heat transfer, what does the slope mean? It means how much heat I am adding or taking out of the system, okay? And this physically relates to a heating rate rather than a fixed temperature. And in practice, if you're in a lab, it's much harder to achieve fixed temperatures than to achieve a fixed flux or a fixed rate of heating, okay? Because that's just easy. You can't just control the temperature. So in other words, over here, I'm going to specify the slope, but I don't know what the temperature is going to be. The solution is going to find the temperature for me. If the slope is 0, what does that mean? It means I'm insulating it over there. If dt by dx is 0, there's no heat passing through. So I would have effectively insulated over there. If dt by dx is positive, then heat is being added. If dt by dx is negative, then heat is being taken out, okay? Now, our discretization is still this guy, Ti minus 1 plus et cetera, okay? This is still valid at all discrete points. However, we need to do something different at the Newman boundary. So at the Newman boundary, we don't have T to say I'm going to put T at n equals something. I have dt by dx. So I need to use two things. I need to see if I can apply this formula at the boundary. It is valid at the boundary because we're assuming the boundary still obeys that same physical law, that same physical model equation. So what happens if I apply this formula at the boundary? So I'm applying it at Tn. It's going to use what? Tn minus 1 is going to use Tn. But then there's this Ti plus 1. It's going to use Tn plus 1, which doesn't exist, right? So if you take this formula and apply it at the last point, what is going to happen? You're going to have a Tn plus 1, which doesn't exist in my solution. You say, oh, let's add a point then. But then you apply it at that point, you're going to get to Tn plus 2. And what do? You have like this closure problem. It's an infinite regression. It's like God is in there, right? It's like you don't know where to stop. Well, let's do this. Let's imagine there is a fictitious point. We actually call it ghost point. You can go in the literature, in the highest top caliber journal. You say, we approximate the temperature at our ghost points. It's hilarious, right? It's ghost points. We call them ghost points because it's only a mathematical step, temporary, to allow us to figure out what equation we need to solve at the boundary. So if you think about this, here I know the equation is T1 equal T left. I know the equation here, I know the equation here, etc. I don't know the equation here. It has Tn plus 1, but Tn plus 1 really doesn't exist. So we're going to keep it for a second, but then use one more piece of information that we have to eliminate this Tn plus 1. Remember, Tn plus 1 doesn't exist. It's a figment of our imagination. It's our imaginary friend. We're going to use it and then ditch it. Okay, sorry, imaginary friend, but you have no feelings to be hurt. So, okay. Then we take our Dirichlet condition, Newman condition. Remember, dt by dx at n is equal to beta. Now, what if I convert this to a finite difference approximation? What does it do? It relates Tn plus 1 to Tn minus 1, which is part of my solution anyway. Agreed? Which is part of the system of equations. So then, if I invert this and get Tn plus 1 in terms of now beta entered the system, which is the value at the boundary for the slope, and now I express Tn plus 1 in terms of Tn minus 1, which is part of my solution. So now if I take this Tn plus 1 and substitute it here, then I get this. I no longer have a imaginary or ghost point. Everything is in terms of quantities that we're solving for, but the equation looks different at the end point. So I added this term over here that's going to go to the right-hand side, and I added another Tn minus 1. So notice the coefficient for Tn minus 1 now became 2. So that's why with finite difference, I say every problem you have to figure it out on its own. Every problem is going to require its own discretization. Because I can move this and put it here and put Dirichlet on the other side. It's going to change everything. I can tell you here, don't use a central approximation. Use a second order backward approximation. It's going to change everything. You have to work it out per problem. But you have to do the math first. We're just building the system of equations, and this is it. For I equal 1, T1 is equal to T left. That's given to us. For any interior point, from 1 to n minus 1, we have this formula, right, the standard one. And then at I equal n, we have this other formula. And this is a system of linear equations. What do? We put it in matrix form. Now, that's similar to what we did with Dirichlet conditions. We have 0 and a bunch of 1s on the first upper, 1 and then this coefficient here on the main diagonal, but I still have this term over here. It's no longer 1. It used to be 1 over here. And this used to be 0 with the Dirichlet condition. Correct? Now this is 2. Yes?
Well, there are, for some of the equations, it was like fi plus 2. Would you have to do like 2 ghost points?
No. So what you would do in that case, yes. So if you were to use, so your colleague is saying, if we were to use for your second derivative, if you were doing I plus 2, that's a second order forward difference, then yes, you would have to spill out. But that's a bad idea. What you would do instead, stay central, because it's a more compact stencil. But then what you could do here, instead of this approximation, you could relate Tn to Tn minus 1 and Tn minus 2, instead of going to Tn plus 1. Okay, but this would be a first order approximation. Okay, unless you get to more points, but that's one option to do it. Here I'm giving the option that is still central, that's balancing. There are issues when you go one-sided only, because you're getting information from one side only, and that's a problem when you are doing diffusion, because diffusion is from all sides. So if you favor one side over the other, you're gonna get wiggles in your solution, issues with the solution. So that's why we always try to be central with diffusion. So you'll learn this if you take the advanced numerical methods course. With advection, it's the other way around. With advection, because advection, it's one directional, from one direction to the other, you favor one side, you do one-sided differencing. Anyway, that's another can of worms. Thanks for asking. Okay, I will tell you the discretization to use. Okay, I will tell you, but that's a good insight you got there. Okay, so then we have just this system of equations, and you just kind of plug it in. We know how to solve this. I don't know, you want to do it in Python? Let's do it in Python. Okay, let's do it in Python. Let's grab your Jupyter notebooks. All right. Bless you. All right, so grab a Jupyter notebook and let's see, where am I in differential equations? Okay, so let me create a new notebook. So fall 2025, heat BVP with Newman conditions. With Newman condition, sure, it's one condition. Okay, so I'm going to grab my boilerplate. So by the way, I saw many of you in your homework assignment, like you keep kind of building out that boilerplate. I don't mind that, but it will be costly for your notebooks. Okay, when you pull in an entire library, like if you're not using Solve IVP or Quad or Integrate, don't bring, or FSolve, just comment those out. So keep the full boilerplate, but if you're not using it, don't pull them in. They will slow down your notebook, okay? They'll occupy memory, literally. So just keep the minimum boilerplate possible that you need. All right, so here for this problem, let's put 100 points, number of points, and then x0 is 0, and then L is 1, so that's domain length. And let's see, this one has to hide. Okay, good. And we're solving that problem here. I need H. Okay, so let's see. H, let's say, is 1.0. We'll vary H in a bit. And then my left temperature is, let's say, 300 K, so 300 Kelvin. So that, excuse me, that's T left. I need beta over here. Beta, and let's say equal 10. We'll play around with this once we build the solution. X is length space from x0 to L with n points, and dx is simply x1 minus x0, right? That's my spacing. My lower diagonal is 1s, and then the last value is 2. So let me put it this way. You guys in the back seeing okay? No? Yes? Okay, anonymous poll. Are you guys seeing okay in the back? And minus 1. And then lower diagonal, last point, I'm going to make it 2. Okay? So that's my lower diagonal. It's 1s and 2 at the last entry. My main diagonal is minus 2.0, minus 2.0 plus h times dx. Agreed? Okay, but now this is a single value, right? So I need to multiply it by np.1s of size what? N. And then fix the first entry in the main diagonal, which should be 1. Agreed? md0 is 1. And then finally, upper diagonal is mp.1s of size n minus 1, 2. And the upper diagonal, the first entry in the upper diagonal is 0.0. Correct? And then we build the coefficient matrix, mp.diag, lower diagonal minus 1, plus mp.diag, main diagonal 0, plus mp.diag, upper diagonal 1. Okay? And you can print it, etc. Finally, for the right-hand side, it's minus h times dx times dx times T infinity. Oh, I need T infinity. What is T infinity? Okay, so let's put the left temperature at 100 and T infinity 327.1. Okay? All right, so T infinity, or actually 5, no, that's the T infinity, yeah, from the heating environment, right? So that's the, let's say we're heating the material, okay? 500, so times T infinity times MP dot 1s of size n. We fix the first and last point, RH as 0, so I'm building this vector over here, this array, this guy. The first entry is T left, or TL, and the last entry, I have to fix that. I already have minus H delta x squared T infinity. I need to subtract from it 2 beta delta x. So I do minus equal 2 times beta times delta x. If you're not familiar with this symbol, minus equal or plus equal, this is equivalent to saying RHS minus 1 is equal whatever is in RHS minus 1 minus 2 beta delta x. Okay? So already in the last value of RHS, I already have minus H delta x squared T infinity, correct? So when I built this here, I filled all the entries. This one all the way to the last one. I fixed the first one, okay? But the last one already contains this. So this statement says the new value in RHS at the end is equal to the existing value minus 2 beta delta x. This is not a math formula. It's a memory formula, okay? So this minus 2 beta delta minus equal does that. If you don't like this, just write it down as RHS minus 1 equal minus H delta x T infinity. If you don't like that, just do it this way. Okay, it'll be the same answer. Okay, you can do it this way if you want. Okay, we're done with this. Okay, great. So now let's solve this. Solve is mp.linalgebra.solve, right? And then a right-hand side. So solve is mp.linalgebra.solve, a right-hand side, and then plt.plot, x solve, and then plt.grid, and let's see what's happening. Okay, so it solved it. It's h minus, did we miss a sign? This t is equal to 100, t infinity, and then we said beta is 10. If we say beta is minus 10, and it's going to try to bring it down, something is off here. Something is off. Wait, there's a mistake somewhere here. Hold on. This doesn't make sense to me. This stinks. Something is off. T infinity, beta. Okay, minus 100. Hold on, give me a second. Okay, so T infinity is 500. Did I make a typo? Yeah. Yes. Thank you, Thomas. If you don't have a Thomas in your class, get a Thomas in your class. Thanks, Thomas. Okay, perfect. So we had a little typo, messed up the results, but it didn't make sense to me because this should be heating, right? And then it was dropping down, it was looking weird. Okay, so how do we test? So on the left, we figured out our temperature. It's 100. How do you test on the right-hand side that you got a Newman condition? So here I have a Newman condition minus 100, so the slope should be negative. So we should be going down. It is going down, but I'm not sure it's minus 100. It's kind of weird. You have to go and calculate it to tell. Or one good option I can try is set the slope to 0. When the slope is 0, it should go flat, right? So if we do that, oh, there you go. It's trying to go flat over here, right? It's trying to match that Newman condition, okay, over there. And you can play around with this, get like different temperature profiles and so on, and change the temperature. Anyway, but that's the point here. So Newman conditions allow you to represent a heat flux or a flux of something that you are specifying at the boundary, okay? I have two examples next for you that I'd like you to just do on your own. And in this case, I have a different differential equation. U double prime equal x squared u. Okay? This is similar to the one we did before, except now I'm putting a Newman condition on the left-hand side rather than the right-hand side. And the right-hand side has a Dirichlet condition, and I ask you to do the discretization. So again, for boundary value problems, there's no canned technique. The only technique is use finite difference to convert the ODE to a system of linear equations or nonlinear equations, okay? But you have to do it per problem. It's problem dependent. Now, as the more you do, you can see it right on because you've done a lot. The more you do, you can see it quickly. So I advise you to, at home, just go through this exercise or use it as a guideline. So that's one problem. These used to be activities we would do in class, etc. But you got all the answers here step by step and the system of equations, and you can solve this in Python as well. This is another one that used to be as an exam problem. But in this case, I have what's called the advection diffusion equation. Again, I promise you I'll teach you more about the physics and the meaning of these equations later. But diffusion and advection are the principal mechanisms of transport, of moving information in macroscopic systems. In your blood, you take medicine and your blood flow is going to distribute it in your body. And some of it is going to diffuse and some of it is going to be advected. So this is a classic advection diffusion equation with constant coefficients. So D and U in this case are constant. This determines the strengths of diffusion. This determines the strengths of advection. You will learn later that diffusion is always associated with a second derivative, and advection is always associated with a first derivative. This is telling us that here heat or temperature, or heat specifically, is being communicated at a molecular level by molecules talking to each other. They're like vibrating. Here, take some vibration from me. This is taking temperature like, oh, forget about your molecules. I'm just going to move you all with a bulk velocity, with a bulk fluid motion, okay? Putting again, remember the example of the incense or like the drop of ink in a cup and letting it diffuse slowly or stirring it. When you stir it, you're bringing in a speed and you're moving by the gradient of the temperature. You're moving the high value to the small value by the speed u. Okay, so anyway, this is another system. Now, in this case, I have fixed temperatures at the boundaries alpha and beta. They're Dirichlet condition. But this problem, you have to also discretize it. And I highly recommend that you do this example at home. And then this would be your discrete formula. You use a second order central for diffusion and second order central for the first derivative for advection. Now, you need to keep order. You need to maintain order across your solution as best you can. Otherwise, your overall method, so your overall error in the entire problem is equal to the highest error you have even at one point. So in this case, if you do a second order method on diffusion and first order on advection, your overall method is going to be first order because that's going to be the worst error you're committing. Okay? So you should always try to maintain the same accuracy with all your discretization. Doesn't matter if you choose. Now, if you are okay that your method is first order, then yeah, do second here and first here. Now, there are pros and cons for using second and first. You don't have to worry about those. This should just work as is for these types of problems. And then you will build the system of equations. So please do this exercise. I don't need to remind you, you're grad students. Do this exercise. But again, the procedure is the same. You get a system of algebraic equations. In all of these cases, they're linear. You can have nonlinear systems, which you also did in your homework, 3, I think, or homework 2, for large nonlinear systems, right? You already did this for a nonlinear system of equations. But the point is you have to apply the discretization per problem. I could add 17 derivatives there and make the boundary conditions dependent on everything else. You just have to trust the math and do it. There's no one way. You have to apply the technique. You're learning the technique. You're learning how to fish, right? You're learning to that's a good analogy. You're learning how to fish with these techniques. All right, let's get back to this. We'll be done in no time. So boundary value problems can be nonlinear as well. You could have the second derivative or the derivative terms can have nonlinear coefficients inside them. Okay, so for example, if the diffusion coefficient depends on the temperature, this would be different. It would be d by dx of k of t or alpha of t times dt by dx. So you still can discretize that. It's a little bit more involved, but you can still, typically all of these derivatives, they can result in a nonlinear term, but they can also result in linear terms. But generally, the nonlinearity could come from the source term, what's on the right-hand side. This is a problem that you did in your homework assignment. All I'm doing here differently is showing you the discretization. So in your homework assignment, I gave you this. I told you this is the formula at each and every point. Build the system of equations, and you built it and you solved it, right? Whereas where did I get this from? I simply replaced this continuous derivative with a finite difference derivative. That's it. That's all there is. Okay. I assume you did your homework. You all got, I think, like in the 100. So that's pretty good. And then because this is a nonlinear equation, right? So you're thinking about ti minus 1, ti plus 1, ti to the 4. Okay, so that's nonlinear. But even if you had ti, so let's say here you had ti times ti minus 1, it will still be nonlinear because ti minus 1 is an unknown, but on the next equation, right? But ti is also unknown. Their product makes them nonlinear. Okay, so it would still be a nonlinear equation, even if you didn't have t to the 4, but you had ti times ti minus 1. You're coupling 2 points in a nonlinear fashion. So it will be nonlinear. If you can't write it in a matrix form, it's a nonlinear equation. Okay? And then you write them in residual form. You move everything to the left-hand side or to the right-hand side. And you need to write the residuals for the Dirichlet conditions. So T1 equal T left, the residual is T1 minus T left. Same here. Tn is equal to right. You write the residual. Same thing if you had a Newman condition. And you get a large system of nonlinear equations, which you did in your homework assignment. And you have the, I don't know what to say here. And that's about it for boundary value problems in one dimension. Okay. So with this, we close almost the topic on tools. We touched a little bit on math and physics, but the next, what's coming is we're going to dig deeper into the great conservation laws. We will start with a review on vector calculus, integrals, the great theorems for vector calculus, surfaces, fluxes, divergence, curls. If you want to review those over the weekend, that will be great, so you'll come in ready. But we will spend maybe 2 to 3 lectures on going through that review. I used to do it by hand on the board, but this year I'm going to convert them into slides so everyone can have a copy for posterity as well, and because we're doing this remotely. And then we will hit finite volumes and how these differential equations show up. We will look at the meaning of diffusion, advection, and reaction, and start developing intuitive understanding of those. And then we want to solve them. So my objective is not only to remind you of the math and the physics. We'll do some analytical solutions, some intuitive understanding of these mechanisms. But my objective is to get you to solve partial differential equations, not only in 1D space. So you'll have time and 1D space. I want to do time and 2D space, because that's where you get the exciting physics. We can go to 3D, but we don't have the time. It will be more time consuming, just even the solution methods. So 2D will be reasonable enough to do. And then you will be ready for mass transfer, because then you can hit the ground running there. You'll learn the physics, but you have the tools to solve these equations. Your homework 5, don't skip it. Do it. You have the tools to do it. It's your first partial differential equation. It's not that hard. We will use solve IVP to solve a system of ODEs. That's it. You'll derive an ODE at every point. So you'll then look at change in time and space together. So that will be our tool moving forward. And then we're going to upgrade that to get to doing it in 2D space. So we look at unsteady heat equations, for example, advection diffusion in 2 dimensions, and all sorts of fun stuff that way. You'll get to see these colorful graphs, the contour plots, and animations. Okay, so I want you to get to, again, I'm focused on tools that will solve these problems, but to do the next step, we need some good background in math, okay, and physics. All right, I'll see you next week. Have a great weekend. Godspeed. Thank you.